Hello everyone, this is a recording for Lab 7 of ENL270 on field effect transistors. So in the previous lab, Lab 6, we looked at bipolar junction transistors and we looked at the behavior of an NPN BJT. In this lab, we're going to look at the behavior of a field effect transistor. In particular, we're looking at an enhancement type MOSFET or eMOSFET. We're using one with a similar package to the BJT in the so-called TO92 outline, again with 3 leads representing or providing connections to the drain, gate, and source. The first thing we're going to do, I'll look at just the characteristics of our transistor. So as we talk about here with an enhancement mode transistor, we're primarily looking at this K value here, which provides some enhancement of the amount of current that flows through it compared to the voltage we're controlling it with. In this case, we have this K value, which is effectively some sort of gain or some proportional scaling value, and we have a threshold voltage, which is essentially where the transistor switches on and starts conducting. Below that threshold voltage, we see no conduction. So the first thing we're going to do, following the lab instructions, is set up a circuit shown in this image here, where we are going to profile or measure the current flowing through the drain as a function of the voltage across the gate source. Here we have the source grounded, so the gate source voltage is just equal to the gate voltage. To do this, we're going to need 2 supplies. We want to set our drain voltage at 10 volts and have our gate voltage variable. I have set up this circuit here. I'm using the breadboard to do this. I have set up this right-hand most supply, in this case to be 10 volts, and the left-hand one to be one I can vary, and provide them both with a common grounding connection. Again, you can do this however suits you to make sure you provide a common ground. I then have 2 multimeters set up, one to measure the gate voltage and one to measure the drain current. So what we're going to do is switch both of our meters on. This to measure the drain current, and this to measure the gate voltage. And we're first of all going to switch on both of our supplies. And we're going to set the gate source voltage to be 2 volts. You can see that in the red meter here, this is the gate source voltage. So I'm going to increase that up to 2 volts. There we are, 2 volts. And then I can measure the drain current using the ammeter here. We can see that's about 30 milliamps for this transistor. Again, that will vary depending upon your transistor. You may get quite different numbers there. So we're going to record that current, and that is our what we're calling our ID on, so our drain current when our transistor is on. We're then going to adjust our gate source voltage until our drain current drops to 10 microamps. So we're going to treat this as our cutoff for this transistor. To do that, I'm going to need to change the range on our ammeter as well as decreasing the voltage at the gate source. I find the easiest way to do this is just to turn the gate source voltage all the way down and adjust the range on the ammeter. Bear in mind that MOSFETs have a small amount of capacitance in them, so if you come from above that voltage and decrease it down, you may need to drop all the way down and then come back up. That's why I find it a little bit faster to do it this way. What we can then do is slowly start increasing this gate source voltage until we see an increase in the drain current. So I'm going to increase that. Suddenly I see now we're at 1 microamp of drain current. So now I can use the fine control on the voltage power supply to have a little more control over this voltage so I don't overshoot. Increase the voltage, increase it up until we get about 10 microamps of drain current. And you see that will vary and decrease slightly, both due to that capacitance I mentioned, but also due to thermal characteristics. So don't worry about getting it to settle at 10 microamps. That won't be worth your time. Close enough to that will be fine. So this is about 10 microamps. And you can see for this transistor at about 1.21 volts VGS. Again, that will vary depending on which transistor you're using. This is not global for all of these transistors. So we're going to note that down as our threshold voltage, VT. We could then compare that threshold voltage to the value in the datasheet. If we look at again, the very end of this lab, you will see there is an excerpt from the datasheet for this transistor. And here you can note down the rated gate threshold voltage, as stated here, with a minimum and maximum value. And we can compare that to what we just measured and see if that seems to correspond to be within range. We can then, using our measurement of a drain current when our transistor is on and a gate source voltage, use equation 7.2 to calculate the value of K for our transistor here. So what this next question is asking about. Knowing that value of K, we can then predict what the drain current should be for three other VGS values of 1 volt, 1.5 volts, and 2 volts, 2.5 volts. We've already measured 2 volts. Note that 1 volt may be below the threshold voltage for your transistor. For example, in this case, our threshold voltage we just measured is 1.2 volts. So 1 volt VGS is below that threshold voltage. You can still calculate and produce a value for the drain current because we have this quadratic relationship here. However, physically speaking, we will not get any current flowing. That is more of an artifact of the model we're using. So below the threshold voltage, we assume there is zero current flowing. So bear that in mind. Once you have calculated those values, what we can do, similar to the BJT, is take our transistor. If you take that to the very front of the lab, you'll be able to run some characteristic curve testing for this and produce something that looks similar to this kind of graph. Again, what you get will depend upon your specific transistor. Here we are plotting the voltage here. We are applying a variable gate source voltage from 0 to 3 volts, and we're plotting that against the drain current we get here, again shown in milliamps. You'll notice this will saturate at about 150 milliamps. This is a limit set on the tester because these transistors are only rated up to 200 milliamps of current, so we put that limit there as just a bit of safety. Okay, what you can then do is take your characteristic curve and plot on the drain current and gate source voltage measurements you just produced or calculated at those different gate source voltages, and see how well that corresponds to the measured curve here. Once you've done that, you can then see if that corresponds well and comment upon any discrepancies in accuracy if they exist. The next thing we're going to do in this lab is consider and look at a switching application for our transistor. So a lot of the time when we use MOSFETs, we're using them as a type of switch. So we're running them between what we call cutoff when they're fully off and saturation when they're fully on. This is the most common use for them in many different applications. To do this, we're going to build the circuit shown in figure 7.4, this circuit here, where we have our MOSFET here, some kind of 10 volt supply, a resistor in the drain here, a red LED, and we're going to provide a square wave into the gate of the transistor. Note that this square wave is a unipolar one, so it's from 0 volts up to 3 volts. So when you set it up, you'll need to make sure that you appropriately set up your waveform generator. As an example, I've set that up on this oscilloscope here using the wave generator. I've set that up to have a 1.5 volt offset and a full peak-to-peak amplitude of 3 volts. That way it would go from 0 volts up to 3 volts and back down again. I've arbitrarily set the frequency to be 8.5 hertz. It doesn't really matter what you set that to. If you set it very low, it's going to be a little bit hard to get your oscilloscope to trigger nicely. If you set it too high, you won't be able to observe the circuit physically working, in the sense you won't be able to see this LED operating. So don't set it above 10 or so hertz probably. Before we actually use this circuit though, what we can do is do some calculations to figure out what our drain current should be in both cases when the circuit is running and when it's off. So we're thinking about when our input voltage is high, so gate source voltage is at 3 volts, and when it's low, so when it's at 0 volts. And we're calling those the on and off state of this transistor and thus this circuit. So when the transistor is on, when it's conducting, we can use what we know about the voltage drops in the circuit. We know there's an ohmic law for this resistor here. We're told there's a 1.6 volt drop across the LED, and we're told there's a drain source saturation voltage across this transistor. That is, even when the transistor is fully on, there is still a small voltage across the drain source junction there. So using that and what we know about the behavior of this transistor, we can figure out what the drain current should be when the transistor is on and when it is off. We can then build the circuit, and if I switch the power supply on, you will see here I am measuring on this oscilloscope in yellow the input waveform, this input square wave, and in green the output square wave where we're measuring across the drain source here. Note the source is grounded, so I have the oscilloscope probe just connected to the drain of the transistor. And we can see here, we put in a square wave, we get out a square wave, and you may be able to see the LED flashing here. That's why we don't want to set the frequency too high. If we set it really high, we won't be able to see the LED flash. So that is our circuit operating. What we can then do is replicate or produce these waveforms. Again, you can sketch those by hand if you'd like to, or use the Benchview application on the lab computers to capture and print out those waveforms, same as we did with the BJT. Once we've done that, we can then move our oscilloscope probe over to the point labeled V2 on this circuit diagram. So V2, you'll note here, it's after the resistor, but before we go through the LED, so at that node there. I do that and just adjust the triggering slightly, just to help stabilize the waveforms on the screen. You can see here, we are still measuring what looks about the same, but you'll notice that the output waveform, the green one here, is shifted up above ground a little bit, because there is still some voltage drop going on in our circuit, even when this voltage is at its lower side. So what we can do is take a measurement of the voltage at this node, which is the voltage V2, and use what we know about Ohm's law to say, well, if I know the supply voltage, I know the voltage at V2, I know the value of this drain resistor, I can then calculate what the drain current flowing is. Bear in mind, you have two options for which value you use for V2, the high or the low. You'll need to think about what they physically represent in the circuit, and thus which one of those we want to use. So we've now calculated the drain current in two ways. We've done so, first of all, just from an analysis of our circuit, knowing the voltage drops across our components here. And we've done it by actually measuring effectively the voltage drop across this 3.9 kilo ohm resistor, and then calculating the corresponding drain current. So you can then check how well those two drain currents correspond. Are they similar or not? We can also then think about the efficiency of this transistor operating as a switch. And we're going to do that by thinking about the power in this circuit. So the first thing we can do is calculate the power dissipated by both the LED and the drain resistor. Note that this is when the transistor is on. Remember, when it's off, nothing's really going to happen. There'll be no current flowing, and so there'll be no power dissipation. So knowing what we know about the drain current and the voltage drops across these devices, or any similar power and Ohm's law relationships, we can then calculate the amount of power being output by this circuit, which is the sum of the power dissipated by the LED and the drain resistor. So that gives us our output power. We can then add in the power dissipated by the FET, thinking about that drain source saturation voltage, to find the total amount of power being supplied to the circuit. And then we can calculate the efficiency of a transistor, which is the ratio of the output power divided by the supplied power. In essence, we're saying we're supplying amount of power, how much of that is being consumed by the transistor, as opposed to doing useful work across the other components in the circuit. The last thing we're going to look at for our transistors here is their frequency response. As we note here, a limiting factor of using FETs as switches is that they have to drive capacitive loads quite often, and that limits how well they can switch. So what we're going to do is set up the circuit shown in figure 7.6, which I've set up on the breadboard here. We've replaced that 3.9 kilo ohm resistor with just a 1 kilo ohm resistor. We've removed the LED, and we've added a capacitive load, this 100 nanofarad capacitor, between the drain and ground, and that corresponds or represents us driving some sort of capacitive load from this transistor switch. We then set the input waveform, the square wave, to be a 10 Hertz frequency, both the same amplitude and offset. From this, we can then determine a voltage gain of the circuit. Think about this as an amplifier. We have some output voltage amplitude, some input voltage amplitude. We then have some sort of gain. So we can measure that. I'm using the peak-to-peak voltage measurements here. You can use any corresponding measurement. What we're then going to do is, as we've done with our filters in an earlier lab, increase the frequency until our voltage gain drops by that 1 over root 2. So we're thinking we've got some gain at a low frequency. We're going to increase the frequency until we reach that cutoff frequency, which is defined as being the point where our voltage gain drops by a factor of 1 over root 2. As an example, if I increase the frequency in the circuit, you can see initially not too much changes. I just need to rescale the time base as we do this. Increase the frequency, not too much is happening. Voltage wise, going up, going up. As we start to increase more and more, we can see this, instead of being a nice square wave of the output, start to round off. Remember, when we have to charge this capacitor up every time we switch on, and every time the output switches off, we can just discharge that. That will discharge straight into ground. That's not really too much of an issue, but our circuit has to drive the charging of this capacitor, which you can see here, as we increase the frequency, becomes more and more difficult for the circuit to do in the amount of time it has allocated. As we increase the frequency, this will get more and more pronounced, and eventually we'll see the output amplitude will start to decrease. So you can see it's starting to drop off just about now, and that will decrease and decrease as we increase that frequency. So what you need to do is increase that frequency until that cutoff frequency, which remember is defined as being when that voltage gain is reduced by a factor of 1 over root 2. In other words, you can figure out from at 10 hertz, what is your gain? What is that gain reduced by a factor of 1 over root 2? And therefore, what voltage are you looking for at the output at your cutoff frequency? And then increase the frequency until you reach that voltage. Okay. As we've noted here, the lower cutoff frequency is pretty negligible. This operates all the way down to DC in this case. Our bandwidth of the circuit is just our cutoff frequency. So once we've done that with our 100 nanofarad capacitor, we can dial our frequency back out again, back down to about 10 hertz or so. Rescale our time base, and then change out this 100 nanofarad capacitor, remove that from the circuit, and replace that with a 1 microfarad capacitor. Bear in mind, this is a polarized capacitor, so I suggest turning the power supply off before you insert it into the circuit, and check the polarity marking on the can. So we're connecting that from, again, that drain node to ground, being our capacitive load. Switch our circuit back on, and we see again we have a similar behavior, but now even at 10 hertz we're starting to see that round off here with our larger capacitive load. We repeat the same procedure as we did before, increase the frequency until we reach that cutoff frequency specified as being that 1 over root 2 point. With this larger capacitor, again we see the same kind of behavior, but it happens a lot sooner than it did for our 100 nanofarad load. Okay. Once you've done both of those measurements, recorded both of those frequencies, we can then actually calculate what the drain source resistance of this transistor is. That's this RDS value shown in equation 7.4. We know that we have effectively this circuit represented by this equation. We've got some load capacitance. We have a resistor, which is the parallel set of this drain resistor here, and the resistance across the drain source of the transistor. So knowing our cutoff frequency and our capacitance for two values, we can calculate what the average expected value of your drain source resistance is. So what you can do is rearrange equation 7.4 to solve for RDS, calculate that for both of those cutoff frequencies recorded, and take the average of those to get your average expected value for them. Okay. The next thing we've asked you to do is, with that 1 microfarad load capacitor still connected, change that input frequency back down to 10 hertz. You'll need to rescale the time base again. And then again capture that waveform either by sketching it by hand or print it out using the BenchView application. Again, make sure things are well labeled. What we can then do is use the cursors on the oscilloscope to estimate the 10% to 90% rise time of this particular circuit with this particular capacitor in here. What I like to do for that is first of all adjust the time base and maybe use the horizontal dial as well, so you get a really nice view of this rise here. You kind of want to zoom in a bit by expanding this out a bit further. You may find you need to adjust the time base the other way. Really what we wanted to do is zoom in on this rise here. That's the bit we care about. So expand out a bit and adjust the oscilloscope until we get a nice view of that. And as you do this, you may find you need to adjust the triggering a little bit. So I'm going to set this to trigger on channel 2 and just lower or increase that trigger level until we reach what we're looking for. And you probably will need to adjust this on the screen again as a result. So there's a bit of fiddling around until you get what you want on the screen. Okay, now we've got a pretty nice zoomed in view of our rise here. We can think about, we know what the base voltage or the sort of low voltage of this is. We know what the high voltage is. What we want to know is where is 10% of that, where is 90% of that. We could then use the cursors here to move the cursors around on the screen. So use the X and Y cursors to mark where those locations are, both in terms of the voltage, where that is here, and then use the X cursor to find out where that time is. And what we want to know is what is the time, or how long does it take to go from 10% to 90%? What is that time value in there? And that is the rise time of our circuit. We then can use this estimate that the rise time, this 10 to 90% rise time, is approximately 2.2 time constants of this circuit. We think of this as being like a low pass RC filter. There is a relationship shown here between the cutoff frequency and the time constant. So knowing the rise time and the relationship between rise time and time constant, we can use this to also estimate what the cutoff frequency should be for the circuit with that 1 microfarad capacitor loaded in there. We can then compare this calculation for the cutoff frequency of the 1 microfarad capacitor to the measurement we did before using the voltage gain of the circuit and see whether they correspond or not, and which method you think is more accurate and why. Once you've done that, the very last part of the lab is a table for you to summarize the key properties of the circuit, and then also a little bit of commentary on whether you think a FET, such as this one, is suitable for switching applications. Think about the key properties for summarizing this table here. And also to think about why we want to use a FET to power an LED or to drive an LED like we did in that switching circuit, as opposed to directly connecting the LED to some kind of input signal. For example, here we had a square wave coming from this wave generator. Why would we perhaps use a FET to drive that LED switching instead of just directly connecting the LED to the output of this wave generator? So just have a quick think about that as well. And that is the last part for this lab.